Hello everyone, welcome to Vibrations and Acoustics. In this problem we're going to figure out what the equivalent spring constant is for this system, which is basically two pulleys connected to two springs. And what we're going to use is the energy method. So basically we're going to take and find the kinetic energy contained within the system to figure out what the spring constant is. Alright, so in order to find the energy, let's start out with this. So the basic formula for energy is 1/2 mv squared. Okay, well, since springs don't have a kinetic energy, we're actually going to use potential energy, which will be 1/2 k times the distance it's traveled squared. Okay, so which is equal to 1/2 kx. Perfect. Just got to make sure I'm not telling you any lies here. Okay, so in order to follow this equation and get these equivalent constants within respect to x, we need to figure out what x is for each one of these springs. So in order to do that, we need to relate these two springs. You can basically consider them as being in parallel, two parallel springs, because they are directly related through this pulley. No matter how this pulley turns, this spring will move with respect to this spring, which is different from series where they are independent of each other. These two springs are completely dependent on each other. Alrighty, so for the distance traveled by x2, it is going to equal x2 is equal to r2, the radius, times theta. Alright, so we're doing this in radians, which is why this is just theta and r2. If it was in degrees, it would be something along the lines of 2 pi r, which would be the circumference times theta in degrees, so that however much you turn, whatever fraction of the circumference you turn, that's how far this x will spin, if you want to think about it like that. How far that x will go. However much of the circumference you basically unwind from that circle. But since we're in radians, this is the basic equation for it. Pretty easy. x1 is then equal to r1 theta right here, because you have the smaller r and it's connected to this. You're still moving the exact same theta, so you can go from there. Alrighty, so now we need to relate these in terms of forces. So F2 is equal to K2 times X2, which is the force caused by a spring. And then F1 is equal to K1 X1. Perfect. All right, now to extend this a little bit, since we have x2 and x1 defined, we'll just go ahead and go to K2 R2 theta is equal to K1 R1 theta. Okay, and that's the equivalent force that we have there. Okay, so now moving on here, using the energy method, what you have is 1/2 k equivalent times theta squared, kx squared, which is equal to 1/2 k1 x1 squared plus 1/2 k2 x2 squared. Alrighty, looking at it like this, you can see that the 1/2s will cancel. Kx we have defined from above here by this x1 and this x2, and we'll sub that in just a second. And then the thetas will, oh wait, too early. Alright, so let's just go ahead and put that x in there. So theta squared is equal to k1 of x1 r1 theta squared plus k2 of r2 theta squared. That theta, that squared will go into theta here, so we cancel that, cancel that, cancel that. So k equivalent is then equal to k1 r1 squared plus k2 r2 squared. And that is your equivalent spring constant for this rotational system. So you go through, find out what the x's are, and you can go through then stick those x's directly into the energy equation and then solve out for KEQ. If you happen to need forces, if you want to use like the force method on this problem, this is what this is for. So this was kind of an extra step that we didn't really need for this problem. But if you are using force method or using energy method, it will be dependent on what you need here. Either way, you need x to figure out what the spring constant is.